In this video, we're going to look at exceptions to the octet rule that we covered in Lewis theory, and we're also going to look at bond energy. So the majority of our compounds we looked at will want to have a complete octet, but there are exceptions to those rules. One exception to that rule is if your compound has an odd number of electrons, such as nitrous oxide. If you have an odd number of electrons, one of those electrons has to be unpaired, and we call that a free radical. And free radicals are really bad. They ruin a lot of the cells inside of our body, DNA and proteins. And so one of the reasons why we have to eat antioxidants is that antioxidants will donate electrons and neutralize that free radical. And there's certain compounds that will form free radicals, incomplete octets. Boron's a good example, BF3, BH3, there's only 6 valence electrons. Aluminum can also do that as well. Also, elements and compounds that end in the d orbital can have more than 8 valence electrons, or 8 electrons in its outer shell. And that's just because they are in that d orbital, and d orbitals can hold up to 10 electrons, so it is possible to have more than 8. But again, most of the time when we're dealing with atoms, we're going to be dealing with octets. Alright, let's talk about covalent bonds now. That is how atoms are connected. And we can talk about strengths of bonds in terms of energy, specifically bond energy or bond enthalpy. And that is the amount of energy required to break a bond. And when you form bonds, you get energy out of it. And by looking at how many bonds you're breaking and how many bonds you're forming, you can calculate delta H of the reaction, which, if you remember from previous chapters, is the enthalpy of reaction, or the heat absorbed or released. Now, there are some very simple trends in bond energy that we can look at. First, if you're looking at bonds between like atoms, triple bonds are harder to break than double bonds than single bonds. That is, it takes more energy to put into these to break these. So if you look at the CC compounds and the CN compounds, we see that trend hold all throughout. Also, the shorter the covalent bond, the stronger the bond is. So here we have bromine bonding with 3 different halogens. F is smaller than Cl, then it's smaller than Br. So the BRF bond is shorter than the BRCl bond, which is shorter than BRBr. So looking at the bond energies, or the strength of bonds, it's harder to break BRF than it is to break BRC than it is to break BRBr. In general, when you go down on the periodic table, your bonds get weaker because your atoms get bigger. And as you go to the right on your periodic table, your bonds get stronger because your atoms get smaller. Now, like I said, we can use bond energies to calculate delta H of a reaction, the change in enthalpy of a reaction. And all we need for that are average bond energies, which we will look up in a table. You won't have to calculate those, but you need to know how to use them. And the equation to calculate delta H reaction is the sum of delta H of all your broken bonds plus the sum of the delta H of all your bonds formed. So broken plus formed, right? Now, if your delta H is positive, that means you're breaking more bonds than making them, usually. And so you're taking in heat from the surroundings. And if you're taking heat within yourself, you're endothermic. While if delta H is negative, that means you're releasing heat and you're usually making bonds. And if you're releasing heat, heat is exiting you, you're exothermic. And let's see how we can actually plot this graphically. So we have CH4, which is methane, plus chlorine gas. The first thing we're going to do here, what this schematic is showing you, is that you're breaking one carbon-hydrogen covalent bond, and you're breaking a chlorine-chlorine covalent bond. You're breaking bonds, and this takes energy to break bonds, so delta H is positive for this reaction. Now we have free atoms, so what we're going to do is we're going to combine a hydrogen and a chlorine together, and this chlorine and this carbon H3 compound to make hydrochloric acid plus CH3Cl. Here we're forming bonds, and so if we form bonds, this is an exothermic process. We release heat into the world. And the two bonds we're forming are release more energy than the breaking the two bonds takes. So overall, we have a net release of energy, and therefore this whole reaction would be exothermic. And that is how we can use bond energies to calculate delta H of reaction. With that, I will see you in the next video.